All right, so good morning, everyone, and welcome back. Here we go to the last session of the Environmental Bioethics course within the program of Bioethics at St. Thomas University. Beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you for your many blessings in the midst of trials and difficulties of life, and particularly now with this extraordinary situation of the coronavirus throughout the world and in our local region here, South Florida, still spiking. We ask your inspiration, Lord, that we may always live according to your divine will, because we understand and we realize that you always want what is best for each one of us. It may not be what we want, but it's definitely what we need. And so we ask you to help us to live responsible lives as we seek to get over this crisis one way or another. And also for the responsibility that we have toward those who surround us. Continuing to focus on these environmental issues, Lord, we ask your guidance. We know that this is also long-term, but again, a sense of urgency because of what is known as the anthropogenic factor, right? The fact that we are the only species capable really of destroying the whole planet, at least the environment, the life that exists on the crust, if not the actual planet itself. And so we know that you are with us, Lord, and we take comfort in that and courage to move forward in the days and years ahead. So always we ask for those who are in most need of your divine mercy at this time. In the name of Christ, our Lord, amen. Father, Son, and Holy Spirit. All right, so today we're going to, someone else, hold on, admit. Okay, I'm glad I get the little window. So today we're going to be looking at climate change and the consequences for humanity and the environment. Now, this is also a culmination, right, of all the previous lectures. The first, at least the first 5 or 6 lectures we spent on looking mostly at the natural environment, the abiotic factors and the biotic factors. Then we looked at the human enterprise, as it were, with energy and energy sources, being that the fossil fuels seem to be one of the major offenders today with regard to an impact on climate. And then finally, last lecture on human population and population growth. All right. So all these factors built into the complexity of the topic of climate change. All right. So as always, we have to make some clarifications first, and then moving forward, we're going to look at the topic itself, global warming, and the ice melting. We realized that the vast majority of fresh water on Earth is held at the poles, at both poles, mostly Antarctica, but also the North Pole. And when those caps start melting, they have a dramatic influence on the climate of the rest of the planet, right? Because of the natural cooling effect that they have. I'm just going to reference briefly the Hadley cells that move from the tropical region to the temperate region, to the polar region, and those 3 sets of Hadley cells influence each other, and in turn they influence the climate pattern of the world. So the 2 refrigerators, natural freezers that we have on Earth at each pole, when they start melting, they may have a dramatic impact on the rest of the climate of the world, okay? One evident impact is sea level rise, but also we're going to look at the scale of sea level rise so far and then projecting forward. Statistically, we're going to be going back and forth from a deterministic model, which is our real life existence on Earth and everything else, to probabilistic model of projections and estimations and models and ratios and so forth. Another real impact is ocean acidification from the CO2 mostly, CO2 mixing into ocean water. So we'll look at that and the impact, which results one way or another in the loss of biodiversity, okay? And then in the second half of the lecture, mostly we're going to look at the plans that we have been doing the past, I'm going to restrict it to the past century and mostly the past half century. And then God's plan, what we may glean that he is expecting of us today. All right. So moving forward then. First, the big picture. As you know, I always like to look first at the big picture and then zero in on more details, time permitting always. But the climatologists, climatologists and archaeologists and paleoanthropologists, paleoclimatologists, and geologists, all right, all of these different scientific endeavors that look at the past of the Earth and the big picture of the past have determined or estimated that we have had at least 5 major ice ages in the first half of the Earth's history, all right, the past 2.5 billion years, more or less. Remember the Earth itself being about 4.5 billion years from the time of accretion. And again, sticking with the big picture, what I'm trying to do here is to show you, at least at the beginning, that there has been climate change and drastic climate change over eons on Earth, and we have had nothing to do with it, okay? So kind of jumping to the conclusion there, but let me give you a little evidence for that. These 5 ice ages that have been estimated from geological deposits and sedimentation, some of what is looked at, for example, is ice cores, right? And the different sedimentation rate of CO2 that is trapped there. At the macroscopic level, we're talking about macro bubbles of CO2, and then other telltale indirect evidence of warming and cooling of the Earth. So we have these broad, very broad cycles that in this scale cycle in the billions of years and millions of years, okay? And notice, of course, that the y-axis, that the x-axis, right, the independent axis, which typically represents time, because time passes on whether we like it or not, it's not to scale, all right? So, for example, from here to here is 100 years, but then going further back, here is 1,000 years and 2,000 years, and so it's compressed. It's not a linear scale. It's more of a log scale, logarithmic scale in reverse. Instead of expanding it, instead of contracting, it expands. Okay, so we have to compress, and that's just to see if we were to compress this second half of the curve here, we compress it into millions of years, we'd lose the effect. Okay, all these would be very rapid. But I have another scale further down that is in the hundreds of thousands of years that will show this in greater detail. Just to point out that at least in the second half of the Earth's history, there have been at least 5 major ice ages going back and forth between freezing and thawing. And certainly we had nothing to do with that, right? So some consequences of, rather some causes, some possible causes that influence the Earth to cause this drastic climate change, these cycles of freezing and thawing, all right? At least 3, for example, which relate to the Earth's orbit, what is known as eccentricity, which is going around the sun, right? It's also known as the translation of the Earth. There's a rotation of the Earth on its axis, which is every 24 hours in an arbitrary unit. And then there is the translation of the Earth, which goes around the sun, again, every 365 days. And that is not an arbitrary unit. That is an actual unit of a day defined by the 24 hours, all right? But at least one rotation around this axis. So then there is also obliquity, which is the tilt of the Earth, the angle of the Earth on its axis, because the Earth is not sitting vertically perpendicular to, let's say, an imaginary line to the sun or the planetary system, right? Many planets have an obliquity like this, and we have one. So that angle also has an effect on the climate change and these cycles from thawing and freezing. Also, what is known as the precession. The precession is another interesting phenomenon of the Earth, which is the wobble around the axis as we rotate around the axis of the Earth, right? Spinning. It's similar to a top. Remember when I was a kid, I used to play with tops. We used to play with yo-yos and tops back in elementary school. And once you spin the top out of the line, out of the string, the top will turn on its point for a while, but then it will start wobbling. It will start turning away from the center of axis until eventually it falls to the ground. That particular wobble on the top is caused by friction of the point on the surface, whatever surface it is, of where the top is turning, and also gravity pulling, constantly pulling on that top, right? So that eventually falls off and collapses. If the top were able to maintain its speed and no friction, it would continue to rotate in principle indefinitely. But this wobble is a wobble, but it's different because it's not the gravity of the Earth itself that is causing it. It's other phenomena. It's a complexity of other phenomena. You can imagine the different eccentricities of the different planets of our system, just the 8 planets that we have, the minor planets, the major planets, and so forth. As they come closer or further away from the Earth, they have an accumulated influence by their own gravity, by the radial gravity radiating out from that planet, just like our planet has, the gravity of our planet has an influence on other planets, okay? So there's been a constant tug and pull on the Earth back and forth as the planetary system goes around. So really, when you think about it, it's a very dynamic system. It's long-term and it's slow motion, right? Very slow to our human scale of, let's say, 100 years, which is a very long age for the human. It means nothing in astronomical time. So we have to understand that these astronomical phenomena and cosmological phenomena occur to the tunes of millions of years and hundreds of millions of years and billions of years, okay? But they do have an effect. They have an accumulating effect. And so all of these forces influencing the Earth have caused a wobble, which is increasing, by the way. As the wobble continues to increase, and if it might eventually cause the Earth to spin out of orbit, okay, to spin out of its eccentricity, which would make us either collapse into the sun or fly out into space. Now, that's the bad news. The good news is that it may take a few other million years to do that, or maybe hundreds of millions of years, who knows. I guess astronomers have done some estimates of that, going into statistics. but certainly we're not going to be around in the flesh here. We may see it from above, hopefully sometime, all right? But all these phenomena of the Earth's orbit itself have an influence on these cycles, and we had nothing to do with that, right? Absolutely. Then also within the Earth, going away from the orbit, also we have significantly plate tectonics and continental drift, of which we spoke about already in the geophysics part of the course. And that has an influence. It's still going on today. That's why we have volcanic activity around the Ring of Fire, for example, that whole, the perimeter of the Pacific rim, the Pacific Ocean rim, right? And the dynamics, again, in the scale of a smaller scale, typically thousands of years, that this continental drift is occurring, seafloor spreading, etc. But all this volcanic activity also has an influence on climate. Remember the primitive atmosphere, for example, was much higher in CO2, so it was a much warmer climate naturally back then. And it was under those conditions that life actually emerged, okay, in a tropicalized Earth, what we call a tropicalized Earth, much warmer and much more unstable than what we experience today. And again, that climate, that atmosphere, going back about 4 billion years ago, would be very toxic to us today. Okay, so even life also has evolved from that original atmosphere into the atmosphere that we have today. So again, a dynamic system. It's just that the scale is long-term. The scale is typically in the thousands of years, hundreds of thousands, millions of years, and sometimes even billions of years of this climate dynamics, this climate change. So we can say that the climate has always been changing on Earth because it's a dynamic system, right? Everything, really, the standard is change. The standard is dynamics. Mm-hmm. All right, so also the ocean currents have an influence on the climate for sure. Again, referring back to the gyres, the oceanic gyres and the Hadley cells and so forth, Coriolis effect, all that interaction that we've seen before. All right, so none of these events are under our control for sure. And yet there has been significant climate change on Earth for many, many, many years and eons. If we zero in within the past 500,000 years, all right, we see that there have been at least 4 major glacial and interglacial periods. Okay, so now this scale is centigrades, and I've shown you this scale before briefly, but you can see it here again, 0 degrees, so above 0 is beginning to thaw, water, right? And below 0, of course, water freezes into solid ice. So here are the 4 cycles, 1, 2, 3, 4, and this is where we are right now. So there's noise going back and forth, up and down. So when we take the average of this, the slope seems to be stable around 0 degrees. So it's anybody's guess where it's going to go, except for the fact of what is influencing this, this trend, right? At least at the level of the atmosphere, is the amount of carbon, in the atmosphere. So here is a comparable scale with ice volume from high to low, and you see that they match up with the melting going above 0 degrees, okay, matching the melt of the ice. So we have these cycles of winterization, tropicalization going back and forth. Now, this data is coming mostly from NASA, where we have, in the past 500,000 years, here on the scale, the cycles of CO2 that have been estimated, again, like I say, mostly from ice cores, right, in the two poles, and looking at those microscopic bubbles of CO2 trapped in the ice. They can be dated. These ice cores can be dated chronologically, and then whatever sediment is found there. And there also is, they look at other things that have accumulated in there. For example, spores from vegetation, and they can tell if it was a more tropical rainforest type of vegetation, or if it was a temperate forest, or if it was a coniferous forest of a cold climate winterization effect, all right? So that's another thing that they look at, the spores that are trapped in these ice cores, etc. But following CO2, at 1950s, more or less, it started to skyrocket, essentially, going beyond the 400 parts per million, and we've talked about this ppm already, parts per million of CO2, where it had not peaked beyond 300 up until middle of last century, okay? Now it's lagging a little, but basically it is following this dramatic rise here, is following the Industrial Revolution, essentially the past 200, 250 years of the Industrial Revolution. So again, I point to the steam engine, which was one of the major inventions of the Industrial Revolution. It allows for industrialization, going from a cottage, what is known as a cottage industry, in other words, mostly handmade stuff, cargo, things, objects that we accumulate, all right, including the production of or processing of food and clothing, etc., going from the cottage industry to actual mass production in series with mechanized, right? That also had all kinds of social impact of displacing the laborer with mechanics, with robots, and the beginning of the social encyclicals of the church with Rerum Novarum, the new reality, back at the end of the 1800s, I think it was 1890s, right? Rerum Novarum was the first social encyclical of the Catholic Church, addressing precisely industrialization and the effect, positive and negative, mostly negative, on the human population. Okay, no time to look at it, but please do look at it. These are the social, the documents of the Catholic Church that speak about social teaching, social justice at the level of the Pope encyclicals, right? Which, you know, the encyclicals are the documents of the Catholic Church that have the highest authority because they're written by a Pope, obviously with a lot of consultation and a lot of teams of experts and peritae experts that counsel the Holy Father when he's writing these documents. Okay, so we see this dramatic increase that associates with the Industrial Revolution. This is CO2 production, again, because the steam engine is being run by heating water to the boiling point, and the fuel that is used for heating that water typically is a fossil fuel, either solid, liquid, or gas, coal, petroleum, or natural gas. Moving forward, here's a reference, you can get more details there, okay? Now, when I started the program about 4 years ago, one of the factors that motivated me was precisely environmental bioethics, which is one of the pillars of the program. The other pillar being human life bioethics, the issues of, like we covered, beginning of life, end of life, and hopefully in the fall we'll look at healthcare also. But back then with the first cohort, we were using another statistical system that is called R, okay? And in my participation in the course, I developed this graph, which I'm just giving you the punchline of a semester's work, an accumulation of data. But basically looking at the past 30 years, which is the time that I had to look at the data, coming from various sources, official government sources, NASA and other sources. But here's just basically the bottom line. I am associating 5 issues here. Population growth the past 30 years with CO2 increase in the atmosphere, with temperature rise, with sea level rise, and with ice melt, okay? Ice melt, or amount of ice, rather, amount of ice left on the, this is just the Arctic, by the way, this is just the North Pole. Okay, so look at human population growth here in the red. Look at the slope of these lines, okay? Now from stats already, we know what the slope is and so forth. So these are all positive slopes except for the sea, except for the ice. So population growth, a positive slope for sure. And also CO2 level, not as dramatic as the population growth rate, but also a positive slope, all right, on CO2, which is in black. Then look at temperature. Now temperature has more wiggle, yearly wiggle. Why? Because, well, we have summer and winter, right? We have summer, winter, spring, and fall. We have the 4 seasons in the temperate region. Of course, in the tropics, we only have basically summer. In the poles, we have basically winter. But then that 2 middle bands, more or less latitude from the 30s to the 60s, approximately, north and south latitude on Earth, we have the 4 season cycle, and that's why the green line wiggles back and forth on a yearly basis. But if we draw a slope of that line, remember this is the actual data, this is actual raw data, okay? If we put a slope on the green line, we see definitely a positive slope, all right? Okay, and then sea level also back and forth. This has to do, the sea level more or less correlates with the seasons also because the atmosphere temperature influences the sea atmosphere, the sea temperature, especially in the upper hundreds of feet, okay? By the time we get down to maybe, I'm gonna take a guess, maybe 100 feet or, well, maybe more, maybe 500 feet, maybe, I don't know, 100, 200 meters down, there's less and less influence from the atmosphere temperature to the ocean temperature. At some point, we get down to a depth, maybe about 1,000 meters, maybe 1 kilometer, where the temperature stabilizes, and it's about 4 degrees centigrade, just above freezing. Okay, so the bottom of the ocean has a stable temperature, which is about 4 degrees centigrade, just above freezing. And why? That's a good thing. It doesn't freeze because of the salinity, because salinity actually lowers the freezing point, okay, of water. At any rate, this dark blue line also wiggles back and forth, more or less following the atmospheric temperature wiggle, all right? But anyway, if we draw a line, a straight line, the slope of the dark blue line, we definitely also get a positive slope, okay? And then finally, the the Arctic ice that is left, Arctic ice, okay? Notice that this has a negative slope, slight but significant negative slope, meaning that there was more ice on the North Pole in the 1970s than there is now in the 2000s, in the 30-year span, okay? Now, you can say that this is a very low negative slope, right? Very low negative slope, but it is definitely negative. And this little melt, let's say a relatively little melt of ice, is in part contributing to this more drastic rise in sea level. All right, so a little melt can cause more sea level rise. And that has to do with the shallow parts of the Earth. If we look at the coastline of the Earth as a whole, I have some videos and maps to show you about that later. But if we look at coastlines throughout the Earth, right, some coastlines are very dramatic, like the Pacific coast of the US. But some slopes are very, very shallow, and like the Atlantic coast of the US. And typically here in South Florida, going offshore, the continental slope goes off shore for about, I think it's about 200 miles or something like that. So there's a very gradual drop, right, in some parts of the earth, the coastline. And so a little rise of sea level can have a big impact on those low-lying areas, basically low-lying areas, all right, which should be the most affected. What else did I want to point out here? Okay, also I want to point out that the same similar phenomenon, just like we have a little melt of ice of the poles, can cause a more dramatic rise in sea level. The same, a little rise in CO2 can cause a more dramatic rise in temperature, the green, okay? So CO2 black rise, and temperature green rise. You can see that these two slopes are different. This is a slight positive, the CO2 is a slight positive slope, but the temperature rise is a more dramatic. So again, the case is that what I'm trying to point here is that it's not linear, it's exponential. A little rise in CO2 gas on the atmosphere, because of its greenhouse effect, causes a larger rise in temperature, and so it's logarithmic. It's not linear, right? It's not a 1-to-1 ratio. It's like an x squared. It's x to the n ratio, all right? Y, in other words, the temperature rise is equal to x CO2 to the n exponential. All right, so that's a concern, big concern. All right, further evidence, if you want, you could go to this site of NASA, okay, and simply punch it. I'm not going to take too much time for these. But this is a site from NASA you can explore. Here's the graph that I exported, and it gives you all of the evidence that has been collected so far. For example, this is 35 years, so that's why I restricted my search to about 30 years, where I had actual good raw data by the numbers on a yearly basis, okay? So you can explore this site further for the evidence on each one of the topics with references and everything. Okay, moving forward. I want to show you a little bit of the evidence in videos of the Arctic melt and Antarctica also, the two poles, the two freezers of the Earth. And then Greenland, which is the third major one, because Greenland essentially has a huge ice glacier. It has the largest glacier on Earth, sits on top of this island called Greenland, which also has an impact on global climate change, okay? And one that perhaps we don't normally think about, which is horizontal gravity, all right? And this is a very rare but real phenomenon. Okay, so let's go here first. Oh, I have to change now. Hold on, let me stop this and change here to optimize share for full screen. Okay, now something strange happens when I go to optimize for video. I think that the PowerPoint becomes blurry or something like that. So be patient with me, okay? We can't have it both ways. We either see the video in some degree of resolution or we look at the PowerPoint. We're gonna see the video now. In case it's too blurry, you always have, of course, you know, I send you the PowerPoint itself at the end, and also the links to all these videos, okay? So you can go back and forth and see them in greater detail or better resolution in your own PC. And I suspect that some of this also has to do with the particular PC or computer that you have. its own capacity at the local level, all right, on your end. And that's also why I'm recording here, by the way, from St. Thomas University again, because there's better internet and better equipment here. So let's do this now. And full screen. Okay, here we go. Sound. Oh.
1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed. What we expect to be a solid mass of ice is actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, senior research scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around, it moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older. And particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old in the bright white, has almost virtually disappeared from the Arctic Ocean. And the Arctic is now dominated by younger and thinner ice.
Okay, let me stop for a moment and just get a little bit of feedback on the video. Did it work okay? Were you able to see it and hear it clearly?
Yes, yes.
Okay, super. Thank you very much. So at least one was able to do it, so I figured. All right, now let's see. So that was the Arctic, right? The ice cube that is sitting there without a continent underneath. Now let's look at the South Pole, which is the actual continent of Antarctica, where we have really the major amount of ice, natural ice. Mm-hmm. And again, I'm going to do the same here. And Maximize this, and now optimize, and maximize. Okay.
NET Television production.
Antarctica is the iciest place in the world. There's so much ice here that only a few valleys in all of Antarctica are virtually ice-free. Everywhere else, ice encases the continent. But Antarctica's icy cover is deceiving. Surprisingly, much of this ice is on the move. Antarctica may appear to have a single coating of ice, but not all the ice on the continent is the same. The majority exists as ice sheets that cover the land and slowly move towards the sea. From Land's End, the ice continues to move as ice shelves that extend over the sea. And beyond the ice shelves is seasonal ice that freezes the sea in winter and thaws in summer. Polar researchers use the three types of ice to detect how Antarctica affects global climate. 600 miles from McMurdo is the West Antarctic Ice Sheet Divide, the high point of one of the world's largest ice sheets.
We're a mile above sea level, and even though it's incredibly flat, there's actually 2 miles of ice below us. Most people think of this as just snow. My colleagues and I, this is a collection of chemicals and gases that are characteristic of the climate when the snow fell. Now, the snow here never melts. It just piles up layer after layer and gets finally compressed into ice. But in order to see those layers, you have to go underground. So let's check it out. It's a lot like looking at a very high-resolution photograph of how climate has changed in the past. You can really see the different layers in the pit. So this is 1 year's worth of snow accumulation, and there's a second year's worth of snow accumulation here below it. And we can figure out what the climate was when that snow was deposited.
Researchers here are drilling cores of ice to investigate Antarctica's climate history. These ice cores contain bubbles of ancient atmosphere.
Real slow. Nice and slow.
Levels of greenhouse gases trapped inside the ice reveal times when conditions were cold or warm.
Good. All right.
We're looking back about 100,000 years back in time, and that goes through the current warm period and the last glacial period.
But ice has existed here for millions of years. And since gravity steadily moves the ice sheet towards the sea, even the oldest ice can tell just part of Antarctica's climate past.
But the length of ice records only extends back to maybe 1 million years or so back in time. If you want to go further back in time than 1 million years, you have to go with rock records.
Finding the rock layers is a challenge on a continent covered by ice. As ice sheets grind across the land, they swallow up the rock layers that detail Antarctica's climate history.
There's been this erosional bulldozer, if you like, the ice sheet just bulldozing the rocks on the continent. There are no rocks left of the age we're after.
As an ice shelf extends over the sea, the warmer water slowly melts away the bottom of the ice, dropping stones to the sea bottom. So geologists are exploring places where ice has deposited them in layers of rock. The best sites are the ocean basins beneath McMurdo Sound. Here, marine life thrives in the salty, freezing waters of the sea. Over time, different sea plants and animals have adapted to changing ocean temperatures. Geologists with the Andrill Drilling Project will core into the seafloor rock layers to learn how long ice sheets have existed on Antarctica and how ice here has affected global climate.
Right now, Antarctica seems to be locked in a very cold climatic condition. That wasn't always that way.
Andrill geologists are not studying the ice itself. They're using sea ice or the ice shelf as a platform to support a rock coring drill rig. They're sending a drill through the ice and down nearly 1,000 feet of water to bore into seafloor rock layers. But drilling on ice is challenging. First, Andril will drill on the McMurdo ice shelf. Although it looks like the ice is frozen in place, the ice shelf is in constant motion.
We're sitting on this floating body of ice, 600 feet thick. It goes up and down once a day with the tide, a metre or so. It's moving to my left at about 150 metres a year. One of the problems we have, if this ice freezes onto our drill string and it goes up and down with the tide, it's just going to rip it out of the ground all the time, and we won't be able to get any core.
So Andril engineers created a hot water drill, a moving ring that shoots jets of steaming water to melt a wide hole through the length of the ice shelf. The hole allows Andril to continue drilling as the ice shelf moves more than 70 feet during the 3-month drilling season.
And so what the drillers will do is deploy it on an angle and anchor it into the sea floor, and then the ice shelf will have moved over the top.
Then, Andril will drill on thin sea ice.
We're standing right now in the southern part of McMurdo Sound. Seasonally, this region will break out. The sea ice that we're standing on will melt out.
Just 20 to 26 feet of sea ice supports Andril's massive drill rig.
We have a drill rig that weighs 40 tons. That's before we add any drill pipe to it. So we add airbag flotation to compensate for the weight of the drill pipe that goes all the way to the sea floor, and we inflate that progressively as we add more pipe to it so that we can continue to drill effectively.
Andril's drilling innovations on sea ice and the ice shelf will reveal a continuous record of Antarctic climate conditions since the continent plunged into a deep freeze. To learn more about Andril's climate research, watch these episodes of Antarctica's Climate Secrets.
Okay, so you notice that very different setting, even though they're both huge ice chunks, the Arctic and the Antarctic, very, very different settings because of the continent that is actually underneath Antarctica, all right? And so there's, each one provides its own information, but as that ice, well, two things, it also goes through cycles back and forth, even on a yearly basis, seasonally, and then in longer cycles than a year also of deposition and melting. But there's a natural melt that is occurring. The challenge, of course, is that rise in CO2 that is causing an anthropogenic melt. Anthropogenic mean caused by the human, all right? I want to focus also on another one, the third one, which is Greenland, because this one is a little more dramatic, showing the melting that is occurring there. Greenland, which it would be like the third chunk natural ice on Earth, certainly not as large as the Arctic or the Antarctic, but still significant and very significant enough to influence the weather. Okay, so again, let me go back to optimizing here and then maximizing here. And
when most people imagine the surface of the Greenland ice sheet, they picture a vast plain of blowing snow. In fact, it is a very wet ice-scape, and it's covered with streams and rivers and gullies all filled with rushing blue water. But the real shocker is that every single one of these rivers abruptly ends in a feature called a moulin, which can be a crack in the ice or a round circular portal with which all of the water flowing through the river penetrates down into the interior of the ice sheet. So what we've learned is that the Greenland ice sheet is not a featureless plain of ice. It's more like Swiss cheese, through which this meltwater is able to quickly and rapidly flow over the ice, enter into the ice, and then escape down at the downstream edge to flow to the global ocean. One of the most pressing environmental problems of the decades and centuries ahead is rising global sea level. And one of the leading causes of sea level rise is the melting of ice from glaciers and ice sheets. And Greenland, in particular, is the single largest melting chunk of ice in the world. We know from climate models and weather stations approximately how much melt is being formed on the surface of the ice sheet, but what we don't know is if that water is truly escaping the ice sheet to connect to the ocean and contribute to global sea level rise. So for the past 5 years, I and my dedicated students have been studying this problem using a combination of satellite remote sensing, using very high resolution military grade imaging systems, as well as intensive field work involving deployment of autonomous drifters and drones, tracking and studying one of the least understood hydrologic systems in the world. What our research shows is there is a clear and definite connection between climatological melting on the top of the ice sheet and the downstream outflow of water to sea level rise and floods in the rivers moving over the Greenland coast. There are two take-home messages from this research. The first is the discovery and a new appreciation for how significant these superglacial river networks are for quickly and efficiently removing meltwater off of the surface of the Greenland ice sheet and exporting it to the global ocean. The second is we now know that the fundamental assumption of these models, i.e. meltwater produced on the top contributes to sea level rise at the bottom, is in fact correct.
Okay, so that's another, the third chunk of ice on Earth, of natural ice, that is the one that is melting the fastest, okay? And one may ask the question, well, so what? What if Greenland melts? There was a time during this tropicalization of the Earth that Greenland was actually melted, and it was essentially a tropical island, right? Well, I just wanted to point out also the effect that ice has, natural ice, the chunks of ice have on gravity, all right? Something that is known as horizontal gravity. Because of the solid mass of ice that is there, that if it melts, is no longer there. So that solid mass exerts a gravity. As we know, all massive objects, or objects that have mass, exert a gravity, and a gravity is radial, goes all the way around, right? And so including horizontal gravity. When you look at Greenland in particular, since it's sitting up there on the top of the world, it has influence on Europe and North America. And it has this kind of influence. The glacier, the ice on Greenland has this kind of effect by way of exerting horizontal gravity, okay? A very interesting phenomenon.
Near a melting ice sheet, the
turtle is slow.
Near a melting ice sheet, two opposing effects influence local sea level. A weakening gravitational attraction lowers the sea near the ice sheet, while at the same time, water flowing into the ocean raises it. To take a concrete example, imagine that the Greenland ice sheet suddenly collapsed into the sea. Globally, the meltwater would raise sea level by an average of about 22 feet. But relatively nearby, in places like Scotland, Norway, and Newfoundland, the disappearance of the ice sheet's gravitational tug on ocean water would cause sea level to drop.
Okay, and that, so the last line there was the sea level to drop locally precisely because of the horizontal gravity field that the Greenland ice is exerting on the water, the local water that is around it, the local water meaning the North Atlantic, okay? And so that has an effect on, let me look at Greenland here on the map for a moment. The coastline around it images. Maybe maps. See what happens is it influences Northern Europe. Oh yes. And it influences North America, mostly Canada. The smallest, oh boy. Okay, this is the smallest scale. Control minus. Okay. See, here's Greenland, all right? And you notice that its coastline is more than what is known as the Northern Territories of Canada, not too much population there. On the east side, on the west side, but on the east side, it's essentially all of Northern Europe, okay, all of Northern Europe. And so when this melts, that horizontal tug, that horizontal gravity field, pulling the North Atlantic toward itself, okay, will be lost. And so the North Atlantic, let's say, will level off locally in this region, and that will mean a recession of the coastline for these areas, most significant Iceland, which is right here, which could be several hundred feet away from the original coastline, from the current coastline. All right, so that coastline will recede out because you can see also, here's Iceland. You can see the continental shelf of Iceland. It's quite large. I believe it's an old volcano, all right, an atoll, which is a single volcanic eruption. So this is the shelf, and the water line may recede all the way out here. So Iceland may actually double or triple its landmass, okay, if Greenland melts. So you can see that the effects are complex, varied, and some are somewhat predictable, others are really unpredictable because it is a very complex situation when the three large natural chunks of ice start melting or continue to melt on Earth, basically the Arctic, the Antarctic, and Greenland, all right? So three major consequences is what is known as Earth tropicalization, the loss of current coastline or the change of current coastline, mostly by sea level rise globally, even though locally regions may be affected in the opposite direction, like I just mentioned around Greenland, significantly. But for the rest of the Earth, basically, the rest of the coastlines, it will be a sea level rise. And also loss of biodiversity, okay? Big loss of biodiversity. So here is one final little video on the ice melt that is pretty dramatic. And this is projecting it forward with a computer model.
When I first saw this product, I thought it looked kind of crazy. Didn't really understand what the benefits would be, but I had seen.
Okay, so again, optimize and maximize. This is from a business journal because of the economic impact also of the change of coastline. You can imagine just, for example, for starters, real estate, right? Property that is now on the coastline, which generally tends to be the higher real estate value, at least in the Northern Hemisphere, is going to disappear. And some property that is somewhere in the middle of a state or inland, could be quite a few miles inland, will become waterfront, okay? So that's just one simple reassessment on the real estate, on sea level rise. Many other factors, of course, to consider. Much more dramatic and relevant is the fact that a large amount of the world's population actually lives along the coastline, especially in the Southern Hemisphere, but everywhere, really. And part of that is because many of these people are on a subsistence level of existence where they need the ocean. The ocean actually feeds them and keeps them alive. So many populations of the world live along coastlines. It'd be interesting to see of the 45 megalopolies that I was mentioning last lecture, how many of them are on the coastline, okay? We're talking about 10 to 20 million people gathered in a very small, high density area. Okay, so here we go, a couple of minutes, 3 minutes. Oh yes, so this one has a just a soundtrack behind it. Well, the soundtrack is distracting. It doesn't really, it's just dramatic sound, dramatic music. But notice that what this video is doing is going around the Earth. These are actual photographs, okay? So it's superimposed. Obviously, it's a model, it's a computer model that is superimposed on photographs. So you see here, for example, let me back down a little bit first, as it's coming onto Australia, the first land target, if you will, of the continents. So here's Australia. There's obviously no sea there in the middle of Australia, right? And but keep in mind, this is projecting forward as all of the natural ice on Earth melts. We're talking about, again, the 2 poles and Greenland, and then all the other glaciers that are on Earth that really are not that significant as far as volume, a large volume of water, okay? But the other 3 natural chunks, yes. So it's going to, is that this computer simulation superimposed or overlapped on an actual photograph of the continents of Earth. So when you see land like this, these are satellite images, all right? And superimposed on it will be this trend of sea level rise to a fully tropicalized Earth, where there will be no freezers, no natural freezers left, no poles, no polar ice, no solid ice on Earth, no ice, okay? So the first one to come onto the scene, it will be Australia, which will develop actually an ocean in the middle, where there is now the great Australian desert in the middle here. Okay, so here we go. I muted the sound so I can say a few words as we go along. Notice the cities that begin to disappear or to go underwater, okay? For example, Perth, Adelaide, now in Europe, notice the cities that will start going underground, underwater. Istanbul, Odessa in Russia, this is a Russian port. It's the only Mediterranean port that Russia has. And Mediterranean because from they can go into Black Sea and come out through the Straits of Bosphorus. Excuse me. through the Straits of Bosphorus in Istanbul, in Turkey, between Turkey and Greece, and then come out into the Mediterranean. Venice, of course, will go on the water, all right? Up in the north, again, St. Petersburg will be on the water, Stockholm, way on the water, Copenhagen, London, Brussels, on the water. On the African coast, look at that, more dramatic. Dakar in the middle of the Atlantic. Up in the Mediterranean also, Kuwait City, all these are cities that will go underwater. And a number of these are megalopolis, all right? So Mumbai, it's been known as Bombay, will go under water. I think 10 million people or 20 million people. Calcutta, underwater, another one of the megalopolis. Bangkok, Ho Chi Minh, Hong Kong underwater, Shanghai, Beijing underwater, another megalopoly, Tokyo. All right, now it's going to move into North America, into the American continent. First, South America. Yes, it's going to be mostly on the southern part. Of course, Buenos Aires, a big chunk of Argentina is at almost at sea level, all right? La Pampa, the Great Plain of Argentina, is flat. Rio de Janeiro underground, underwater. And the Amazon basin, of course, is going to flood with salt water, with seawater, which will essentially destroy the Amazon because it will flood with salt water. Now, the coast of, the west coast of South America has the Andes, and so it's much more of a dramatic fall. So it seems like perhaps only Lima, capital of Peru, would be affected with that rise. Later we'll see North America. Let's see where it's going now. Yeah, here we go. Okay, so it's now going into North America, Mexico. This is the west coast of North America. The Sea of Cortez will be nicely flooded in there. San Diego flooded. San Francisco. Let me see if I can make it scale a little small. No, that's the scale of the movie. Okay. Portland underwater, Seattle underwater. Now, the North Atlantic. Check out. Miami, Florida, gone. New Orleans, gone. Charleston. Cuba will be split up into several islands. Havana, gone. All right, look at what's left of the Caribbean. A lot of low-lying areas there. Bahamas practically gone. Puerto Rico reduced. DC flooded, New York flooded, Boston flooded. The Great Lakes may filter in with salt water. So basically, I think there's a little bit of sound here now. That's the end of the track. Okay, so there's no speech here except for what I said, but basically this would involve the melting of all natural ice on Earth, and therefore what the effect would be is a tropicalized Earth, all right? And this is what we're talking about. For example, here is Alaska, currently photographed, and it will start looking like something like this. And that's, I pointed out, that's why we have petroleum in Alaska, is because in the past it has been tropicalized, all right? And this tropical rainforest then with the winterization has collapsed and decomposed and turned into the black gook that we know as petroleum. I'm gonna shift gears a little bit into the acidification of the ocean. In other words, I've been looking mostly at land masses for now, and the effect on land masses with a sea level rise or climate change, global warming. But I want to look now at the oceans, considering that about 90% of the volume of the crust of the Earth is oceans, right? I want to explain a little bit this phenomenon of the ocean acidification. So we have that CO2 produced naturally and also being sunk by nature, carbon sinking that occurs, all the kilotons the gigatons that we looked at in previous lectures. But remember, there's that net positive 4 gigatons of CO2 for the past decades being produced anthropogenically, right? And so that net increase of CO2 is the culprit here by the global warming, but also another side effect, if you will, of that CO2 in the atmosphere is that it combines with water to make carbonic acid, all right? And carbonic acid then dissolves into the ocean. Dissolves into the ocean, changing the pH of the ocean, acidifying the ocean, making it more acidic. Now, it doesn't mean that the ocean is actually going to turn into acid. And we have to understand that, again, to be able to speak with competency, all right? So I just want to explain the pH scale for a moment, because the current pH of the ocean is about 8.2, which actually is alkaline or basic, right? It's a little on the alkaline side for about 1.2 measures of pH, because neutral is 7 on the pH scale. Now, what is pH actually? pH is the amount of hydrogen or available hydrogen in a solution, all right, in a substance, which typically is water. So the amount of hydrogen that is available will make that solution either acidic or alkaline, right? And the scale is from 0 to 14. But this scale, 0 to 14, is kind of an odd scale. It's not really a decimal scale. Where does it come from? All right. And at the end of the day, what is this pH? That P, actually, it's a logarithmic scale. All right. It's an exponent. It's a power. And so the scale is really from 0 to 14. It's an exponential scale. So hydrogen at a pH of 0, right, means that there's no hydrogen, because any amount multiplied by 0, right, is 0. So that is known as the multiplier factor. I have no time to go into it, but the multiplier identity. But basically, any amount to the 0 power is equal to 0. Okay, by convention. Just like any amount to the first power, to 1, is equal to that same amount. All right, so the scale here goes from 0 to 14. And what I'm trying to point out from this is that it's a logarithmic scale. In other words, the net effect is that when the pH changes from 1 degree to the next, or from one value to the next, it's a 10-fold increase or decrease. So if we have a pH of 6, all right, that substance is 10 times more acidic than a pH of 7, which is considered neutral, all right? And the same goes up the scale. If a pH of 8 means that that substance is 10 times more basic or more alkaline than neutral, or pH of 8. And so pH of 9 means that it's 100 times more alkaline. A pH of 5 means that it's 100 times more acidic than 7, all right? Then, no time now, but you can go online and look at some scales and equivalents of what this pH means. For example, the acid in the stomach is a pH of 2 or 3 or less, and that's why it can break down protein. We can swallow meat practically whole, and the stomach will take care of it because of the acidic pH. And the reflux is that heartburn thing, is that pH of 2 or 3 coming out of into the esophagus and literally burning the esophagus, causing that sensation, etc. So this is the pH scale, all right? What I'm trying to say by all this is that a small change in pH, for example, from 8.2, which is the current pH of the ocean, to 8.1 has already a dramatic effect, because this change is a logarithmic scale, all right? It significantly leaches out, for example, the calcium that is available for coral to build itself, all right? Calcium carbonate, because it takes up the carbonate, and then it, by lowering the pH, it sucks out the carbon, the calcium available for corals, and the coral starts bleaching, all right? So one negative effect, big time negative effect of acidifying the ocean, which doesn't mean that it has to go below 7, all right? Just from moving towards 7, from 8.2, which is the current pH, down towards 7 is sufficient already to cause massive bleaching that has been experienced and documented already over the years. And so we go from this kind of biodiversity that is exuberant, especially along the tropical and subtropical regions of the Earth, right? About 60 degrees, about 30, up to 30 degree latitude north and 30 degree latitude south. We have coral growth with all the community that lives there and the ecosystem. Because again, keep in mind that coral is like a condominium, all right? It's more like a city, really. It's a whole ecosystem. And the core, the basis of that coral, of what is known as hard coral, is calcium carbonate, which is the skeleton of the coral, of the polyps, the colonies where the polyps live, all right? And so these condominiums then serve as a housing and habitat and shelter and feeding grounds for many other animals that live in the area, including anemones and so forth. So when the coral goes, the whole community goes, all right? And the whole ecosystem just becomes literally a desert for loss of biodiversity, dramatic loss. So that's real, that's documented. Getting into biodiversity then, let's look at another little video here that explains it better than I could explain it. And I guess oh, I left the optimization, sorry. Okay, well, you have the PowerPoint that you can look at.
It's only a family vacation if all the family is together.
Hi, it's Mr. Anderson, and this is AP Environmental Sciences, video 35. It's on the loss of biodiversity. Way up in northern Norway is the Svalbard Peninsula, and on there, scientists built a giant seed vault. It's protecting the seeds of humanity, our crop seeds, into the future. They chose to put it there because it's protected against tectonic activities. It's really, really cold, and also as the sea levels rise, it's going to be protected as well. The idea was hundreds or thousands of years into the future, we could go there and grab seeds and then start growing those crops again. Unfortunately, we've already had to make withdrawals from that area. And the reason why is the war in Syria put a lot of these drought-resistant crops at risk, and so they've had to take more seeds out and they've moved those to Lebanon. But it does kind of get at this idea of the importance of biodiversity. Biodiversity is not only species diversity, but it can be genes, species, especially our domesticated crops and livestock, and then ecosystems themselves. And they have value. They give us our resources resources, and they also do these ecosystem services. And they're at risk. We're seeing biodiversity loss all around the planet. The causes are habitat loss, invasive species, climate change. We also have overharvesting, and then finally pollution are all impacting biodiversity. And so it's led to conservation. What do we do first? We have to figure out where that biodiversity is being lost. We have to figure out the conservation status of these organisms or areas. And then finally, we can pass laws and treaties to try to preserve a lot of that biodiversity. And so again, why do we need biodiversity? It's where we get our food. It's how we filter our water, energy, medicine. We all get that from our environment. And again, our environment also does these ecosystem services. They keep our climate stable. They decompose material once it's died. They pollinate our crops. And so we need biodiversity on our planet for resources and to do these services. If we define what it is, it's simply a variety. Variety at the genetic level, at the species level, and at the ecosystems. And so those genes that organisms have, once the organism is gone or the gene is gone, it's gone forever. It's extinct. Species as well. These are all the fruits found in a certain area of the tropical rainforest, but also we're talking about the crops that we have. And so I think it used to be we had around 8,000 different types of apples that were being grown, and now it's 100. And if you look in your own supermarket, it's way less than that. And then it's ecosystem changes as well. Once an ecosystem is gone, coral reefs, for example, you can't build that back again. And so what is causing this biodiversity loss? Well, when I was trying to come up with a quick way for you to remember these 5 things, I came up with this mnemonic. And so if you think of the biodiversity COP, and if you think of high COP as a way to remember it, if we put those in order, habitat loss is the first big impact on biodiversity. So deforestation, when we're cutting down those rainforests and planting crops. Right here we're growing soybeans. This is looking from above where we used to have a tropical rainforest. We're reducing that diversity and we're replacing it with one simple crop. Invasive species, this is kudzu. It's a plant that was brought from Asia. These are the zebra mussels in the Great Lakes that they're really wreaking havoc. They came from the Mediterranean. We're also seeing climate change impacting biodiversity. So if we look at the polar bear, for example, will they go extinct? It's hard to tell. But if we look at all the areas where they used to do well, we're seeing a decrease in the optimal polar bear habitat. Also, over harvesting. Humans have been harvesting animals for a long period of time. The dodo is extinct because we killed all of the dodos. And we're also seeing over harvesting now, especially in our aquatic systems. And then we can have pollution. Pollution's impacting the environment as well. So if we look at that Deepwater Horizon explosion, that led to an oil spill, which is impacting biodiversity in the Gulf of Mexico, and it'll take us years to figure out how that impacts it. Now, this has been going on for a long period of time. Extinctions are a part of nature. And if we look back through the fossil record, we've seen 5 major mass extinctions over time, and they have different causes. But most scientists are pointing to right now as the 6th mass extinction. This is mass extinction caused by humans. We're seeing extinction rates that we've never seen before, biodiversity loss that we've never seen before, and its cause is us. And so how do we solve this problem? Well, the first step is to identify where the problem is. And so the IUCN, International Union for the Conservation of Nature, has been around for over a half a century, and what they've done is come up with these different statuses. Extinct in the wild would be one where we maybe have them in a zoo, but they don't exist in the wild. Then we have critically endangered, endangered, and vulnerable. Then we have near threatened, and finally areas of least concern. And so if you go on Wikipedia, you can look up any animal or any plant that's going to tell you its conservation status. So for example, the whooping crane are endangered. The California condor is critically endangered. Humans, you can imagine, are an area of least concern. They've then created this red list where we look at how many of these species fall into these threatened or these red categories. If we look at mammals, almost 20% or over 20% are in this threatened kind of an area, and amphibians are really at risk. And so what do we do? Well, what we can do is pass laws. So in the U.S., we passed the Endangered Species Act in 1973 to protect species and the ecosystems on which they depend. And so it essentially is a list. So bald eagles are a classic example that were added to the endangered species list. And so there, I think, were around 500 breeding pairs in the lower 48, and now there's over 10,000. So once they recover, we remove them from that list. Grizzly bears were added. Their population is coming back. In Montana, there's a big debate right now over do we remove them from the list or not? But it also has to be balanced with human resources as well. So logging, for example, can impact certain species that are going to be found on the endangered species list. We've also seen global changes. The Convention on Biological Diversity in 1992, all of the green countries here signed on that biodiversity is important, it has an economic import, and that we're going to try to protect it. But again, it's not legally binding, and so we're still seeing huge decreases in biodiversity. And it goes back to the first thing I talked about in this class, the idea that the planet supports society, but society is driven by economics. And so we're never going to see decreases in biodiversity loss until there's an economic incentive or a way to do that. And so did you learn the following? Could you pause the video at this point and fill in the blanks? Well, let me do that for you. Biodiversity has value.
Okay, I think we saw enough of the video to get the picture of biodiversity. Let me see if I did that correctly. Yes. All right, so going back to the PowerPoint then. I think he explains it very well, the reasons for biodiversity and how essential it is for even just the survival of humans to have biodiversity, which is a gradual process in nature, but expanding also. Nature naturally tends toward diversity, as we saw even in the first course of the program, toward adaptedness, right? Adaptedness, any niche that is available for colonization, in principle, on average, likely will be colonized, right? Finally, in a little article here, just in a French news item, again, with regards to the loss of biodiversity. So let's go here for a moment.
When I need to grow my business, I use Fiverr. I found a designer for my logo, a programmer for my website, writers for my content. Just search, click, and you're done. I love the results so much, I even got the logo tattooed on my arm. Sorry, wrong arm.
Stop dreaming and find your freelancer at Fiverr.com.
The message is clear. Act now, or the world faces a catastrophe. Scientists already have a good idea which species are most under threat from human activity. Among them, amphibians like frogs and salamanders. Up to 40% of them are at risk. They help reduce the spread of malaria by eating mosquitoes and protect crops by eating pests. A quarter of mammals are also threatened with extinction, including Madagascar's lemurs, driven out of their natural habitats by logging and expanding agriculture. Widespread deforestation is also leading to the loss of species of plant life that could provide potential cures for devastating diseases like cancer or HIV.
We've lost much of our native forests, much of our native wetlands, and effectively biodiversity needs to be considered as an equally important issue as climate change.
Rainforests are crucial to biodiversity. They're home to animals including jaguars, tigers, orangutans, and mountain gorillas. They also store huge amounts of carbon dioxide, which helps regulate climate change. But environmentalists are fighting an uphill battle to save them. Around 12 million hectares of tropical rainforest were lost in 2018. That's the same as 30 football pitches per minute. The fourth highest rate of loss since records began in 2001. Another key concern for scientists, the sharp decline in insect populations. They are responsible for pollinating around 3/4 of the world's crops, allowing the crops to produce seeds that will become the next generation of plants. Researchers say up to 40% of insects could die out over the next few decades. Oceans are suffering too, with overfishing exceeding nature's capacity to replenish fish stocks. Human activity is also putting a strain on coral reefs, meaning that natural wonders like Australia's Great Barrier Reef could soon be a thing of the past.
All right, so I think I've given you plenty of evidence here for reason for concern. A couple of more slides, just some a graph to correlate or to associate at least human population growth in purple with extinction rate. Now there's a background extinction rate that goes on in nature all the time, but you can notice that this is the background extinction rate here, fairly flat, the first half of the curve, but now it's gone into a log phase again, which parallels the population growth of humans. But if we look at the two slopes, again, we notice the difference that the slope, even though they're both positive slopes, the population growth rate is slower than the extinction rate. In other words, this slope is much more steeper. The extinction rate slope is much more steep than the population growth rate, meaning that a smaller amount of increase in human population has a larger impact on biodiversity loss. Okay, again, so even though the two slopes are positive, the ratio is not linear. If it were a linear ratio, we would see them actually parallel, but they're not parallel. We see that the extinction rate is actually a much more dramatic slope, all right? And so it's logarithmic. Again, logarithmic meaning that a small amount in increase in human population, relatively speaking, has a bigger effect, bigger negative impact on biodiversity or biodiversity loss. Okay, so there are a number of organizations now that are looking at this at the local, regional, national, and even international level. Scientists and other policymakers, so forth, coming together to try to figure out what to do in the positive to slow down the loss of biodiversity on Earth, okay? And there is, this one is done by the UN, just last year, had its latest report. If you see, there are a number of acronyms that now you find on the web, and this is one of them, the IPBES, all right, is the measure of biodiversity loss on Earth and what kind of policies we can come up with, scientific policies, to try to prevent that. So this is the report itself. You can, this assesses the loss of biodiversity in the past half century on Earth. So again, I don't want to take time to look at it in detail, but here's the reference that you can take a look. It's from UNESCO of the United Nations. All right, so we are now at 11:10, and in the second part of the lecture, like I explained, we're going to look at human activity, human plans, and God's plan for humanity with regards to climate change and conservation. How do we slow down this climate change, the anthropogenic factor, the anthropogenic portion of climate change, all right? The anthropogenic portion, which part of it is CO2, but not only that, it's also a loss of just surface area of the Earth for farming, for example, or urbanization, and then overfishing and so forth. All of these complex issues, we're going to look at some major conventions and conferences and agreements that have been done the past 50 years, more or less, okay? And conservation efforts even beginning at the beginning of last century, really, with, for example, the National Park Service here in the United States, which has served as a model for many nations of the world to create national park systems also in their own countries, all right? So we're gonna break now for, let's say it's come back at 11:30 and be ready to go for about another hour. Okay, so we'll come back at 11:30. I'm going to pause the recording now. Here we go. Okay, students, and welcome back. Let me see, there is a chat. Look at the chat here. Shaban. Locally, Little Haiti and other nearby neighborhoods are being gentrified and residents pushed out as developers on the water realize that sea level rise poses a danger to their pocketbooks. Okay, thanks for the comment. Yes, there's so the issue of sea level rise is extremely complex. Oh, sorry, let me put on the microphone. Give me a minute. Okay, testing the microphone, yes. All right. The issue of sea level rise, of course, is extremely complex and has many facets to it, many dimensions. Invariably, we have to engage in the dialogue so that eventually policies that are friendly to the environment will be developed, all right? And like I've mentioned many times before, we have a mixed economy, meaning that there's a lot of regulation into the market. So it's not just straight up capitalism of supply and demand, but certainly it is a complex issue, and that's why I'm trying to look at all the different aspects of it. Ultimately, we need to make our own decisions for sure and how to participate in the process. Let me move forward then with the second part of the lecture here, which I want to look more at human endeavor to try to preserve the environment. And so in general, what we call conservation, all right? And beyond conservation, also remediation of areas that have been spoiled and to try to fix them up again. Like I mentioned also in last lecture, several examples of bioremediation in the United States and throughout the world. And I just want to take the story, this narrative back about a century, more or less, to the establishment of the national park system of the United States. And the reason for that is that our national park system has become a model for the world, okay? And many other nations of the world, or several other nations of the world, have followed up in establishing this kind of legislature and areas to be preserved for humanity and for their nationals, for their citizens, generations to come, all right? So the actual National Park Service, as a section of the Department of the Interior, was established by President Wilson in 1916. But the idea goes back before then to President Roosevelt, back about 10 years prior to that, in 1906, when he comes up with this idea of a national park system. Again, I'm not an expert in any of this, so if any of you know anything differently, you can let me know. But basically, just from the little research that I did, we can go back about 100 years here in the United States at the beginning of last century with the national park system. Teddy Roosevelt himself was a hunter. Here's a photograph of the time, black and white, of course, with his hunting outfit. And apparently he was quite an accomplished hunter of big game. He went also to other parts of the world, Africa and so forth, hunting, but here in the United States. And he noticed as a hunter, the loss of biodiversity already back then, okay? Like for example, bison, otherwise known as the American buffalo and so forth. So he came up with this idea of establishing large tracts of land in the United States that would be preserved for generations to come, all right? And as far as I know, there are at least two major qualifications for a national park in contrast to a state park, which can be as large, but typically smaller, all right? But typically a national park is not only a relatively large area, but more significantly, it's a unique ecosystem. It's a unique environment, all right, that doesn't exist anywhere else in the United States. It may be other parts of the world, but at least in the continental or in the United States as a whole, including Hawaii and Alaska, this ecosystem doesn't exist anywhere else, all right? And so that's what qualifies, that's one of the main qualifications for a national park. Like we were talking last lecture, toward the end of it, they are precisely the Everglades National Park, which is not a swamp, and it's a unique ecosystem that doesn't exist anywhere else. It doesn't mean that it has to be pretty necessarily. It's not about pretty. It's about the delicacy, the uniqueness of the ecosystem, all right? Also, Biscayne National Park, which Luis was mentioning, is mostly underwater, and it's off Biscayne Bay in the southern part around the power plant of Turkey Point, all right, nuclear power plant. And then there's also out in the Florida Keys, at the bottom of the Keys there, there's also a national park. What's the name? I forget the name of that one that you brought up.
The Dry Tortugas.
The Dry Tortugas, thank you, yes. Which is squarely into the Caribbean Ocean, beautiful crystalline waters, great diving, et cetera, et cetera. I've never been, but I've heard of it a lot. I have been at Yellowstone, thanks be to God. My brother and sister-in-law lived in Colorado for a while, and while they were there, I would visit sometimes in the summer, sometimes in the winter. And as they say in the US, the Rocky Mountains is the North American playground, right? The American playground. It's a beautiful area, just gorgeous. Any time of the year, any of the 4 seasons. And we did a trip, a road trip to Yellowstone and stayed there for a few days. And I never really understood the whole issue of the geysers and so forth, and the hot water springs. I knew about them from biology because we get bacteria here that are extremophiles. They are thermophiles, meaning that they live in almost boiling water, these bacteria. They actually love it there, all right? Talk about extreme adaptation. Or also sulfur, very sulfurous water, or a combination of both, hot and sulfur. So we get these extremophile bacteria. But I had never understood Yellowstone until I actually went to it, and it turns out that it's a huge caldera. In other words, it is the crater, the now defunct or not active, inactive crater of a volcano, of a huge volcano, all right? And so it's inactive, but because it has cracks underneath the ground into the crust, what happens is the water seeps down there periodically, and as that liquid water hits the magma or close to the magma, it boils. And as it boils, the steam then comes out, gushing out into the atmosphere and causing these geysers. Okay, and Old Faithful is one of them that has been clocked periodically for many years, I think decades, and it's called Old Faithful because it spews out steam on a regular basis, all right, or at least it used to. I don't know if it's still doing it, but that's the issue, that it's a caldera. In other words, is the crater, the inactive, defunct crater of a volcano, which in principle, in the future could explode again, all right? I also remember visiting another trip that I did on the West Coast, the real West Coast of the United States, not the Tampa Bay, to some of the national parks out there, which are just gorgeous, beautiful. If you have time to go, Yosemite National Park, Sequoia National Park, Crater Lake, Olympic Mountain, in the Washington state, and then there is also the one that blew up. I remember going to, it escapes me right now, but there's a volcano that blew up about 30 years ago in the 90s, I think it was, in the West Coast of the United States.
Cascades?
Sorry?
The Cascades? Or is it Mount St. Helens?
Mount St. Helen, thank you, yes, Mount St. Helen. And I was able to go there like a couple years later. It's also a national park now, Mount St. Helen, because of the unique ecosystem that developed from the blow. And it was all like a moon scape. It looked like a crater from the moon, all gray, ash. The logs were, the whole forest were laid down barren on the ground like matchsticks. The explosion was so intense that it stripped off the bark even before the tree was burned to ashes. It stripped off the bark just from the intensity of the explosion. Anyway, massive, massive natural phenomenon that occurred there. And it was such a contrast because I did that Mount St. Helen, like I said, a couple of years after the explosion, which still looked pretty much barren. And I went to Crater Lake, also either just before or just after in the same trip. And it was such a contrast because Crater Lake sits on a beautiful mountain. And also I can see Mount Rainier from the distance, which is just covered with coniferous forest, okay? And such a contrast, but you give Mount St. Helen time, like a few, maybe not even thousands of years, a few hundred years, and it will be covered again with a coniferous forest, okay? Because again, nature is opportunistic, and if there's a foothold, there is going to be a colonizer who will get into it, because there's going to be a pioneer to go into that foothold and colonize it. And then we get the succession that I talked about last lecture. Okay, so it's I've always found it fascinating that nature is expansive that way. Life is overabundant, and if we just leave it alone for a while, it will regenerate and it will continue to grow and expand exuberantly, okay? So anyway, I think that Yellowstone was the first national park created in the United States. So we have Roosevelt and Wilson to thank for that. And to this day, there are several hundred national parks and national monuments and different categories, but they're all run by the federal government, and part of our taxes is going there. So I highly encourage you to visit the national parks in the US because it's quite a beautiful, beautiful sight to behold. Many of these places also are fully equipped. They have showers, they have electricity running. Many of them also have Wi-Fi now. So you can camp out there in style, in luxury, okay? All right, let's move forward now because I'm going to switch gears into international conventions and treaties and agreements to preserve the environment and to try to bring down this issue of global warming by the CO2 concentration, okay, which is the main culprit, like I've been mentioning, for climate change and global warming. Here's just one graph where it shows, again, the association and the parallel between a CO2 concentration, the blue line, the blue curve, and a temperature rise on the green. Again, it's seasonal, so it's more wiggly on the temperature because it's seasonal, whereas CO2 is more steady because whether it's summer, winter, spring or fall, the industry keeps going, right? Okay, so just a little detail about the two types of measurements. The first half of the blue curve is from ice cores. This is CO2 concentration, the blue curve. All right, CO2 in parts per million. And the first half is from ice cores. So it's an average, it's not as wiggly as you can see, but the second half is actually more accurate, if you will, because it's based on actual instrument readings from the 1960s forward, okay? So this is actual direct. We can say that this data, the second half of the blue curve here, this is direct data, whereas this other one is indirect data, like I showed you from those videos of the ice cores that were being drilled in Antarctica, okay? All right, so let me switch over here to a series of international environmental agreements. And these are just some highlights because again, not much time to go in depth into them, but pretty much they begin in the 60s And I'm going to stick mostly to the UN simply because it is that world body that developed after the world wars. Okay, keep in mind that last century, the 20th century, was a dramatic century. I don't know how else to describe it, but it was dramatic because we saw many changes in last century. All right, let's reflect just a little bit what happened last century here that we just left behind a mere 20 years ago. The onset of electricity, for example, and the car, modes of transportation, but also population growth from the 1900s to the 2000s, quite dramatic. Technology, lots of technology pouring into society from, imagine, something as simple as, well, telegraph, for example, all the way to cell phones today, right? Which is an actual microcomputer in our pocket. So, but including the first half of the 12th century, not one, but two world wars, okay? 2 world wars, and they associate with population increase. So it looks like when we start getting too many, we start having problems with each other. And so 2 world wars that were devastating twice again, not only for humanity, but also for the environment and all the contamination that was done by those 2 wars, okay? So then finally, when we get into some semblance of peace and we go into the Cold War between the Soviet Union and the United States, keep in mind that during the wars, we were allies with Russia, okay? And even into the Second World War, Russia was an ally, was part of the Allied forces against Hitler and the Third Reich and Nazism, right? As Hitler tried to invade St. Petersburg, for example, the siege that he did there for about 2 years and killed, decimated the population of St. Petersburg as maybe at least 1 million people who died from that siege. But Hitler was not able to take St. Petersburg, and it cost him a big chunk of his army there. At any rate, right after the Second World War, then Russia started appropriating countries in Eastern Europe and became the Soviet bloc, right? And therefore we go into the Cold War into the second half of last century. Let me see some more chats here. Give me a minute. Okay, we got that one. Siobhan also, mixed economy, my foot. Okay. Back the stack against anyone without money and power. And it is high time people understand the power of corporations, monopolies, unfair growth, and lack of regulation. And giving a pass as a capitalist economy is, to put it delicately, putting one's head in the sand. Okay, thanks for your comment. Fighting the forces of fascism. Okay. Thank you. So basically in the second half of the 20th century, with the Cold War and the Tante and all the stuff was going on there between the Soviet bloc and the US, we get some semblance of peace, okay, even though there's nuclear buildup and deterrence, etc. There are a number of countries that are showing an increased concern for the human interaction with the environment, okay? And it's put under the aspect of human development and the human interaction with the environment. So we're, nations are looking at humans not just on our own, if you will, isolated, but actually associated with the environment, all right? In a particular place that we live. So in the 60s, Sweden petitioned the United Nations for starting some kind of a conference or convocation on looking at the interaction between humans and the environment. And that solidified into a conference on human development that was done in 1972 in Stockholm, Sweden. All right, so that was the beginning, if you will, of these formal conventions and treaties and agreements at the UN level, which, oh yes, what I wanted to mention about the wars is that after the war, there was an effort to unite, and even during the war, to unite the nations for a peace effort. And first it was called the League of Nations. Okay, some of us old enough to remember, of course I wasn't born at that time, but the League of Nations was kind of the precursor for the United Nations. And the idea was that because precisely at the end of the Second World War, we have developed nuclearity, all right? The power, nuclear power, we had harnessed nuclear power and the power of the atom. And then the idea was to use that power for peaceful events, for peaceful research and for peaceful ways rather than for destruction, okay? Because precisely of the potential that it had, for example, one nuclear plant to light up an entire city. And so there were treaties on nuclear power use and so forth to try to gear it toward peaceful ways, peaceful enterprise. And the United Nations comes into being, bringing nations of the world together to work precisely for justice and peace throughout the world. Now, I can also tell you that human beings that we are, these conferences become politicized from the very beginning, all right? Imagine in the 70s and the 80s, we're right into the Cold War. China is emerging as a nation that has, excuse me, I think I have the wrong, give me a minute here. I brought up the older version of this, excuse me for a moment, the document. Let's see. I need to get into my OneDrive here. Updating. Let's see. If this is the document that I need. Okay. It's an older version of the document. I had cleaned it up a little bit, but it will make do for now. I apologize for this. When I send you this document, I'll send you the updated version, all right? But I want to say that these conferences at the UN level was the greatest hope for real change toward the better for the world, for establishing peace and for putting the technological prowess of humanity to good use, all right, for the betterment of all peoples. But it was politicized from the beginning, all right? So we have the Cold War going on in the Northwestern Hemisphere between the Soviet bloc and the US mostly. And then in the Northeast, we have China, the tiger rising also as political and economic and social power of the world, right? And then in the Southern Hemisphere, a lot of countries also bringing in the negatives of colonialism in their countries, colonialism of the past, right? So all of these conferences started getting kind of sequestered by these different groups, ideological groups and so forth. So it was politicized from the very beginning. It made me think that of the definition attributed to Aristotle, the definition of the human attributed to Aristotle, homo politicus, okay. Homo politicus, of course, that's the Latinized translation because he was several centuries before Latin in Greece. At any rate, Homo politicus was his definition of the human, of man, right, philosophically speaking. But in the original sense, a transliteration of Homo politicus is the political man or the political human in today's terms, right? But that political was not partisan necessarily, it was not a partisan reference. Remember also classical Greece, the Republic and so forth. But rather, it was an appeal to the polis, all right? To the let me write it down here since I have this Word document available. Homo politicus. Transliterated. But the reference of political is from the root of polis, not police, all right, but polis. In fact, also police also comes from there, the ones who patrol the polis. But polis is the city, okay? In other words, to live civilized, that's where city also is the core, the root word, city is to be civilized, to live in a civilized way. Not out in the jungle, okay, stabbing each other, but actually to live in a civilized way, basically. That we are a species that is capable of living in a civilized way. In other words, that we can engage in dialogue, in political dialogue, to come up with solutions for the problems that beset us, okay? And so that was the original reference of the political way, is to come up with, today they talk about diplomatic solutions as opposed to violent solutions of aggression or threat and so forth. So diplomatic solutions, which also includes, again, economic sanctions from one country to another, etc. But beyond that, pure, let's say, more virtuous definition of the human, the species that can engage in civilized discourse, all right, to resolve our issues. Of course, beyond that then goes into partisan ideology, and so is certainly less than perfect, because who has the perfect crystal ball, right? Who really knows for sure what the solution is to these problems, being that they are so complex? Well, I can tell you one person who knows the solution, and his name is Jesus Christ. And when he tried to implement that solution, he ended up crucified for it. So that was not a happy ending, humanly speaking. However, on the third day, he proved that he was right by rising from the dead. Okay, so it gives us hope. It gives us hope. And that's why we appeal to Christianity, because we see that it is truly, has a lot to offer. Really, ultimately, the solution is in the way of our Lord Jesus, okay? I'm getting a little bit ahead of myself here, so I just gave you kind of the punchline toward the end of the lecture. But basically, we have the capacity. We can try to put aside our prejudices and luggage that we carry, right? We're all product of our education. How we were raised has had a big influence, consciously and subconsciously. And many countries that I've lived in, even in my time, and the stuff that I've seen, and the poverty and everything else has an impact on one's life. And that's why I decided to become a priest as opposed to having a family, for example, etc. At any rate, back to the capacity that we have for civilized discourse, for civil discourse, okay? That is the best of politics. And the worst of politics is just the ideology that becomes narrow tunnel vision, that will simply not have any dialogue and will not listen to the opposition, not for 1 second, because they absolutely have nothing good to say, right? That's the worst of politics. And we have seen a lot of that all over the place. Moving forward, In the intervening years here from the 70s to the 80s, the UN was looking at other issues, so did not focus specifically on the environment and the interaction between humans and the environment. But there was also background preparation going on for the big conference of the Rio conference, all right? So Rio de Janeiro, 20 years to the year after the Stockholm conference, right? Was actually, this one is known as the Stockholm Declaration, was kind of the beginning in 72 at the UN level. And then in 92, the Earth Summit at Rio, which is also known as the ECO 92, all right? Because of its emphasis on the ecosystem and the environment. Focus, again, this is just very brief highlights because of the time factor, but you can get into all luxuries of details looking up each one of these conferences. I'm going to give you a list of 26 of them right now, all right, in a few minutes. But basically started looking at toxic chemicals on the environment, all right, alternative energy sources, transportation, water, all major issues that we've talked about a little bit, just touching highlights basically. There's a lot in here, but you can see that it's a very ambitious agenda, and that makes it highly complex. And how do you put more than 190 nations together on a single track, right? How to do that? Well, I think we got to pray a lot so that there's conversion of heart and mind to work in one direction. All right, so from the Earth Summit in Rio, also comes out this framework, the UN framework for trying to tackle climate change, okay? Again, the acronym is UNFCCC, so I'm not gonna try to pronounce that, but basically this is the UN framework for trying to slow down climate change. Again, the anthropogenic factor, the anthropogenic factor of climate change, right? Literally to stabilize greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. All right, so this is kind of a punchline of the framework that is established at the Earth Conference, at the Earth Summit of Rio in 92. Then what happens is that 3 years after that, these conferences begin, the COP conferences, okay? Now the COP, because you see this acronym coming up year after year with these conferences, is the acronym is Conference of the Parties. The parties are the member states of the UN that participate in the conference and ratify the agreements. Okay, so again, not every nation does that, but the fact is, the real fact is that the vast majority of nations participating in the UN ratify these agreements, all right? And so those are known as the COP. Those are the parties involved, the Conference of the Parties. And like I said, there's going to be 25 of the 25 so far. We'll look at them in a minute. But it comes out of the framework from the Rio Summit. All right, so one major focus is on reducing greenhouse gases, which again, I've stated repeatedly, is an extremely complex and delicate issue that involves many sectors of society at every single level. So the first COP was in Berlin in 95, all right? I mean, you're 3 years after the Earth Summit of Rio, and then it's one every year. It's one every year because they're trying to assess, every year they're trying to assess how they're doing on reducing greenhouse gases, okay? And that's what it's doing. And after they do the assessment, they come up with resolutions, and then they vote, and they either ratify the resolutions or not. And those are the agreements that come out of these COPs. Okay, so they're going to be listed as COP 1 through 26, actually, which was canceled before because of COVID. And that brings it up to the beginning of this year, all right? Or actually it was, the first half of this year. So here they are listed, starting in 95, and you can scroll down. We're gonna look at just a couple of them further beyond the Rio summit. We're gonna look at the Kyoto Protocol, and then we're gonna look at the Paris Accord, all right? Just as two highlights and see the development there. But basically, they're all listed here. And if you're interested in what happened in each one of them, you can go to the UN website and just punch, or even just in Google, just Google COP3, 4, etc. And you can follow them in luxury of detail in each one of them, all right? I also want to point out that even though they have been, like I say, today 25 and the 26 has been postponed, the number is 28 here simply because a couple of years there were two conferences in the same year. So for example, you can scroll here, you'll see the date repeating. Where is it? 6, 7, 8, 9. Here, 2001, there are two COPs in Germany and in Morocco, all right? And then further down also, there's another repeat of the years. Last year, there was Bonn in Bonn, and then there was the COP proper in Madrid, which was a combination between Chile. Actually, Chile was the sponsor of the conference, but it was done in Madrid, all right, for logistical purposes. And this was just in December of last year, okay? So, and that was COP25. Okay, so let me backtrack for a moment and go back to the Kyoto Protocol, but because this one was quite significant, all right? The Kyoto Protocol was COP3 in 97, just 3 years after they started, 95, 96, 97. And to reduce the onset of global warming by reducing greenhouse gas concentrations, all right? And so again, the anthropogenic effect. This was again in Kyoto, Japan in 97. Then we fast forward almost 20 years to the Paris Accord, just looking at the clock here, in France, 2015, in 2015, okay? That one was COP21. Here, they actually set a goal after all the research was accumulated and studied and analyzed and so forth. The conclusion was that we needed to slow down the global warming by below 2 degrees centigrade. Okay, so this is a number that you see tossed around, 2 degrees centigrade. In other words, if we go beyond an increase of 2 degrees centigrade in the atmosphere, it is almost the point of no return. We will get into a galloping, we will get into a, what is that called? It happens in evolution also, runaway. Just like we have runaway evolution, for example, the peacock and the tail, that animal has become so exuberant, it can barely fly anymore, all right? That's called runaway evolution. Well, we could also have runaway extinction if we go beyond 2% or 2 degree centigrade increase in the temperature of the atmosphere, all right? And that is what they're calling the potential for the 6th massive extinction. One of the little videos mentioned it. There is a fossil record of at least 5 massive extinctions in the history of Earth, of which we had nothing to do with, because the last one was approximately 65 million years ago, and very was the one that is most popular and well known because of the extinction of the dinosaurs, but many other species also went out. And actually that one was is estimated to have been caused by the meteorite that crashed into Earth, and it's been supposedly spotted several miles into the crust of the Earth in the Yucatan Peninsula that caused such a massive explosion that darkened the Earth for several years, shutting down vegetation, and then all the food chain collapsed. Essentially, the herbivores went, and then the carnivores went. And ironically, we could say the demise of the dinosaurs opened up a niche for the mammals, for the rise of the mammals. So that last massive extinction was essentially, again in the big picture, the collapse of the reptile world, which lived in the tropicalized Earth, right? And then the Earth went into a winterized environment, and the mammals surged because of warm-bloodedness and because of hair and so forth. So now we are, the mammals are of some of the predominant groups of animals on Earth, okay, well adapted. And then an offshoot of the reptiles was the birds that also are warm-blooded and live in a more winterized Earth that we have right now. Winterized because we still have significant amount of natural ice on Earth. So we can claim that at least theoretically we are more of into an ice age type of environment than into a tropicalized environment, because we have still on Earth, we have significant amount of natural ice, okay? Water that is taken up in a solid form and therefore unavailable for living, because we need liquid water for living. All right, so anyway, back to the 2 degree centigrade. If it increases beyond a 2 degree, it is considered by many estimates of scientists throughout the world that then we will get into runaway extinction, all right? And that it would be essentially impossible to stop, to reverse it. And that's why that 2 degree has become so critical, okay? We're not doing too well, unfortunately, in the Paris Agreement. Out of 197 nations, originally all signed, but then 2 or 3 actually retreated from the agreement. And I have a little slide on that. So here we are. The nations that have ratified it are 146, plus another 48 that signed. That makes, 194, and 3 that either didn't sign or withdrew. Syria, still under turmoil today. Nicaragua, with its own brutal dictatorship. And of course, the United States, it associates with the change of political party from the Democrats to the Republicans, because it was under President Obama that the United States signed into the Paris Agreement of 2015, right? So he was still the president at that time. Let me just put the year here for reference. But then we have the change in party. So like I say, it becomes ideological. And so President Trump pulled out of the Paris Agreement. And yet we, precisely because we are one of the major contributors of CO2 to the atmosphere, which again is related to our economy, which we talked about ad nauseum at this point, okay, so I'm not going to belabor the point. So that's the current state of affairs there, with the significant conventions. There have been 3 more, let me see, 21 to 24 more COPs. There have been 4 more COPs. Let me go back here just so that you see the reference here is Paris in 2015, all right? Then there was, the next year was in Morocco, in Marrakesh, Morocco, back to Germany, then in Poland, back to Germany again, and finally Madrid. I also want to mention that Germany has taken the lead in Europe, seemingly, at least in continental Europe, with the environmental issue because, for example, they were big on nuclear power back in the second half of the century, precisely, as a product of the Second World War, right? Because not only did we develop nuclear power, they developed nuclear power too. There's an anecdote of some German trains that were going through Europe, and they were stopped at some checkpoint, and they were carrying water, okay? And when they were asked, what was this water? I said, well, it's just water. Yes, but it was a particular type of water because the water was made with tritium, okay? And so we have three main species of hydrogen. The normal hydrogen that we breathe, the single neutron atom. But then there's deuterium that has 2 neutrons, and then there's tritium that has 3 neutrons on the core, on the nucleus. And that is also known as heavy water, and it's radioactive. Okay, and so that water that the Germans were transporting in that train was actually tritium for their nuclear research. So it was not just the Manhattan Project on this side of the Atlantic, okay? And eventually they developed nuclear power too. So like I say, in the 50s, trying to harness that nuclear power for peaceful means, nuclear plants became very popular in Germany and throughout Europe. And so Germany was being powered by nuclearity quite a bit, the whole country. But then at some point, the environmentalists put so much pressure because precisely of 3 Mile Island and Chernobyl, even before Fukushima, that I think the Prime Minister Merkel decided to dismantle the nuclear plants in Germany, okay? And so my understanding now is that they divided Germany into 2 parts geographically for energy sources, okay? And this is a very ambitious goal of Germany, but basically the northern part of Germany is going aeolic, meaning by wind power, all right? And the southern part of Germany is going hydroelectric, right? Because the southern part is more, has the Alps and the runoff of water there and all the rivers and so forth and lakes. And the northern part has the North Atlantic, which is a prodigious sea that has very strong winds and so forth. So essentially Germany is making the transition from nuclear to, well, first they make the transition from fossil fuels to nuclear, and now they're making the transition from nuclear to renewable energy, okay? The northern part again going aeolic, meaning wind generally, and the southern part going hydraulic, meaning river, lakes and rivers, water runoff, okay? So interesting that perhaps Germany is showing us the possible way of making that transition from fossil fuels through nuclear to renewable energy sources. Okay, folks, I see that the chat is lighting up here with 10 chats already. I'm sorry, it looks like there's a second conversation going on between all of you here. Fine, please keep going, all right, on your conversation. I have no problem with it, but I need to finish my lecture because I only have a few minutes, okay? So if I have time at the end, I'll open it up, but feel free to continue your chat so we can actually have 2 conversations going on. One, which is mine, recorded, and the other one between all of you in the.
Excuse me, Father. I understand you want to finish your lecture, but if you look at the chat, I mean, I'll stay for a lot of the things you have are easily found on the internet, Google, what have you, but perhaps we could discuss a little bit more the bioethical implications of the Paris Accord as opposed to just sloughing it aside.
Right, okay, so I'm going right there actually, and I'm going beyond the Paris Accord. I'm actually going to the church's teaching on all this, all right? And so, let me just reverse these. Yes, and precisely during the Paris Accord, or just up to the Paris Accord, before the Paris Accord, let me rephrase myself here. Pope Francis, who, as we know, is a great environmentalist, he took his name precisely based on Saint Francis of Assisi, who was in the Middle Ages a lover of nature, including human nature, and sacrificed his life precisely to help others. So Pope Francis takes his name after Saint Francis to be inspired in part by his love for the environment. He publishes the first encyclical in the history of the Catholic Church, the 2,000-year history on the environment and the poor, okay? They're intricately connected. We cannot read Laudato Si without a concern for the environment and a concern for the poor, the least among us, truly the least among us. And so Laudato Si is even a phrase from the poem attributed to Saint Francis of Assisi that is embedded in the encyclical. It's almost 200 pages long, but it's a small booklet form. So again, I highly encourage you to read it. I have recommended it as one of the texts for this course already, mentioned it even from the start. So do read it, please. Okay, it's devoted. It's in 6 parts. And the first 3 parts basically are the state of affairs currently on the earth with regards to all the anthropogenic effect, negative effect on the environment. And then the last 3 chapters are basically his proposal for a better world, a better tomorrow. Care for our common home. Care for our common home is the subtitle of Laudato Si. All right, and our common home, of course, is planet Earth. So he started working on this quite a few months before the Paris Accord, because he was already following the COPs that were going on. Excuse me. He was following the COPs with great interest and concern. And so he wanted to make a contribution, a significant contribution on behalf of people of faith and belief, and like to say, people of goodwill, right? So Laudato Si had a lot of consultation built into it. Many scientists, sociologists, theologians, philosophers of all different walks of life, even just folk, family members, etc., had input into Laudato Si, okay? Various regions of the world, Aborigines were consulted and so forth. And this is the document that he produced. And he got it out precisely in time for the Paris Agreement, all right, or for the Paris Conference. Because I remember I started my master's precisely around that time as a direct result of that, in part, at least on the environmental side. So let me go here back to Paris for a moment. Where are we? Yeah. Okay, yeah, but I wanted to see the actual dates. Give me a minute here. Yes, so the dates are significant because what I'm trying to say is that Pope Francis published Laudato Si in the summer of 2015, okay? And we were here at St. Thomas following this very closely because we had heard of Laudato Si through the grapevine, and we were waiting for it. Actually, he had finished writing it around the spring of 2015. He wanted to publish it for Pentecost Sunday, but it was delayed a little bit, and it was sequestered. It's not sequestered, it was embargoed, all right, until the summer. So finally, it came out about 2 months after the original date of publication, even though I think it still has the date of publication officially as Pentecost Sunday of 2015. So with great interest, some of us here at St. Thomas picked it up and started reading it and devouring it. And in fact, the development of this master's program was in part because of that. Not only that, we also developed a conference here in 2016 at St. Thomas University. We put together the first international conference on climate, nature, and society in 2016. Here it is. You can look it up on the website. There's a second one. We've done two since. We did a second one in 2019, last year. But the first one, here we go. It was 2 days full of talks. You can see all the professors, all the speakers listed here with their talks. It's all online. I want to point out particularly the first one. Well, the keynote speaker was Cardinal Turkson. Okay, Peter Turkson was actually the convener for Laudato Si. And we had him here at St. Thomas University just a few months after the publication of Laudato Si. Peter Turkson is a cardinal in Africa, and he was the Pope's right-hand man for writing the encyclical. All right, and we had the good fortune of having him here through a lot of prayer and trial and tribulations. That was amazing that we actually put that conference together. But we did, thanks be to God. And so back to the Paris Agreement, right? So in the summer of 2015, Pope Francis publishes Laudato Si. It hits like a bombshell because it's very, very controversial. Needless to say, I've done programs on it. I have a talk for 2 years, paragraph by paragraph of the whole encyclical in Radio Paz. It took over 2 years to go through the whole encyclical 1 week at a time. At any rate, that was to have some level of impact in the Paris Agreement, okay? And thanks be to God, it did. So that the vast majority of the nations signed on to it. Now, here we are 5 years later, still struggling with the issues. It is extremely politicized, but I do want to end up with this one slide here, all right? I can see I'm gonna run into a little bit of overtime again. But there is a site that is also run by NASA that is called the Human Influence Index, all right? The Human Influence Index. And this is a scale here from low to high, low being 0 and high being 64. And the reason for 64 basically is just because it doubles, all right? In other words, the human population ideally, like any other population, ideally doubles, all right? So from 0, we get 1 somehow. From 1, we get 2, 4, 8, 16, 32, 64. So that would be from 1 to 2, 2 is 1, 4, 8, 16, 32, 64. So this represents 6 generations of humans, which would more or less be 120 years, taking an average of 20 to 150 years, 20 to 25 years of the human generation rate, okay? And the last video I want to show you, which is this one. All right, so in this video, again, it is instead of looking forward, it's looking backward and projecting the human population on the globe, on the earth, on the land. See? Again, let me do the video thing here, optimize on this side and maximize on this side. Okay, so it's fairly self-explanatory, you'll see, but the video basically is going to put yellow dots for every million people that rises on Earth since the origin. I think actually starts around, anyway, it starts several thousand years before the time of Christ, and it moves forward into the Christian era for the past 2,000 years, okay? So the narrative is very self-explanatory. Here we go.
An environment is a system of living things. The Earth is our environment. The capacity of our environment to provide space, to produce food, and to supply energy are all limited. Humans thrive on less than 17% of the Earth's surface, and only about 4% will grow crops. We depend on these limited resources for our survival, yet we are increasing our population as if they were infinite. This fact is at the core of our environmental problems. On this map, we'll show population growth from the year 1 CE to the present, and project our growth into the year 2050. Population concentrations will be indicated by dots, each of which will represent 1 million people. In areas where people are spread out and don't live in concentrations of 1 million, dots are placed in the middle of their approximate range. Historical references will be provided by images and text at the bottom of the screen.
But I want to point out that it's going into exponential growth rate now. As you notice, the dots, this is the exponential growth rate that we experience in the human population. Okay, and you can see by the yellow dots, each dot representing 1 billion people, will go up to our current time and then project forward for about 30 more years on the current rate, the current current rate of growth. And then, like we saw from that article from the last lecture, then there's this dramatic drop, mostly by the use of technology, and specifically the one big factor is the use of artificial contraception, which I've spoken already about earlier. I have a couple more words to say at the very end. Okay. Notice how the first density, very high density, is occurring in Asia and gradually moving westward. India, the subcontinent, then Europe, and then finally North America. South America and Africa remain fairly unpopulated compared to the rest. And this is mostly because of mortality rate being higher, less access to healthcare. Okay, let me stop it here for a moment. Less access to healthcare in general, and so higher mortality rate, particularly child mortality rate. Okay, so that's a little more narrative here.
Our population is expected to grow to 10 billion by the end of this century. Yet the Earth's size...
Okay, sorry, so this number 10 billion may be revised now.
At the end of this century.
This 10 billion may be revised now because this video was made a few years ago. And imagine now the new data that is coming out precisely because of the massive use of contraception in many parts of the world. This may have to be adjusted down by maybe 1 or 2 billion, maybe 1 billion, okay?
Yet the Earth's size remains the same. Slowing human population growth and lowering our use of natural resources are key to reducing the impact we have on the planet. Through the decisions we make about our lifestyles, our numbers, and our consumption, we can all help preserve the health and beauty of our home.
I like that this video ends actually with the words of the papal encyclical, the subtitle of Our Home, Care for Our Common Home, right? Which is planet Earth. Okay, so basically it involves human behavior at the end of the day, all right? One way or another, we're talking about human behavior individually and collectively. And that's why I bring it down to what Christianity has to offer us by way of a sacrificial lifestyle that brings really comfort. It may not bring pleasure at time, but it will bring happiness in the sense that we were able to live maturely and responsibly on this earth. This quote from G.K. Chesterton that has been quoted variously in different ways. One way I had heard it is that not that Christianity was tried and failed, it is that it's never been tried before. It's never really been tried. So this is the actual quote here from a book, What's Wrong in the World, all right? And that's the thing, that Christianity, living the Christian values is difficult, it's very challenging. Like, for example, natural family planning, as opposed to contraception. Just pop the pill instead of instilling discipline in that human relationship of the conjugal life, all right? And so very, very challenging in today's society, extremely challenging and complex. Yet, I still believe that because we have been created in God's image, that we are indeed capable of doing it. We're capable of doing it. Unless we're willing to say that the plan of Jesus Christ is pie in the sky and it's totally non-functional and that it's not achievable and unrealistic, then, well, that would actually make God a cruel person, right? It will make him cruel by becoming incarnate and then giving us an example that is not achievable. That the bar is high, you better believe it. As far as I'm concerned, it's the highest bar around, okay? But it looks like now, because we have gotten to the point that we can actually destroy the planet and ourselves in the process, the one alternative increasingly seems to be reaching for that high bar, all right? And so this little quote that I heard at some point, but so long ago that I don't remember any longer where it came from, is a gradual shift from self-centered and other motivated. You can think, for example, of a teenager. When I was a teenager, I was self-centered and other motivated, okay? Like peer pressure, for example, to moving gradually, hopefully, toward self-motivated, getting up in the morning because I need to get up in the morning and I want to get up in the morning and do stuff during the day, hopefully for the good of someone else, and other-centered. Okay, so this is another way of the other center, is that dying to self, instead of going scuba diving this morning and going sailing this afternoon, doing things that actually may help others, all right? So again, I know there's been a lot of chat going on back and forth. I don't know if anyone has a parting comment or question or anything. Go ahead, please. Okay, well, I think you had your own conversation there in the chat, back and forth, fine. So I'm closing with this then, hopefully. Oh, I'm sorry, I had left the thing for optimized. Let me just ask briefly a question. Were you able to see or hear what I said since the last video? Anyone?
Yes.
You were able to hear and see what I said. Okay, so good.
Yes, we did.
Here.
Right, all right. Thank you, appreciate that. So I was mostly on the encyclical. Okay, folks, so you can see that this lecture is the most complicated one, right? Obviously, there are many different viewpoints here. We have to be respectful of them all, for sure. But we have to understand that people have different opinions also of this, and there is no crystal ball, or rather, I think there is one crystal ball. Again, I keep coming to this point because I see value, tremendous value, in the person and the teachings of Jesus Christ. If we truly believe that he is who he is, the Son of God incarnate, then that is the answer, and that is the crystal ball. Now, how to implement that? We know that he had a radical option for the poor, right? And he had very tough words for the rich, but it was the corrupt rich, because he also associated with good rich. They say that perhaps Lazarus, Mary, and Martha were people of means, and he would stay at their home and so forth. So we have to be careful not to do eisegesis with the Gospels and with Scripture, putting into the Gospels scenarios of our own time today, or putting our own prejudice into sacred Scripture, okay? We have to see it in its own context. Anyway, I do believe that the crystal ball is Jesus Christ and his teachings, okay? And that's why when I was in my late 20s, I finally decided to devote my life to that and try to follow in some small way his example. This program and this course is a direct product of that. And as you can see, I'm telling you the history here from 2015, which is when we started the program till today. You are the fourth cohort, thanks be to God. We've been able to keep it alive for 4 years now, okay? And so now what comes is a well-deserved break, because you've been pretty steady and patient and loyal to these talks, to these lectures for about 11 months now, practically every Saturday that we've been gathering, okay? And so now we're gonna take about 3 weeks off into the fall semester, which will start the last week of August, okay? And then we're going to our last semester, the healthcare bioethics, and trying to round up the internship. And with regards to the internship, I also have some more to say about that, but I'm going to do it in a separate context. So I'm going to close this video now, and then I'll develop a separate video to talk about the internship, right? Which pertains to the last semester. Any parting comments, questions, anything on today's lecture or the course in general in environmental bioethics? Anything? Okay, I don't hear anything, so.
I'm good.
All right, I'm going to then stop recording.